Hello, everyone. Welcome to our first ML Real Talk session. I'm Daliana, and today joining with me is Shreya Rajpal. While we're waiting for a few other folks to join, feel free to interact with our posts. Tell us how many experiences you have in machine learning, computer vision specifically, what frameworks you have used, and what are the challenges you have. So today we're going to talk about Shreya's experience with computer vision, and then I will give a quick demo on how you can do computer vision models in Predibase, and then we'll open for Q&A. So if you have any questions, feel free to type in the chat. Yes, it will be recorded. We can send it to you, and you can view it later. We have 23 people here. You can also type it in. Let us know, where are you in the world? Let me stop sharing for now. Okay. All right, let's get started. Are you ready, Shreya?
Yeah, I think so.
All right. Hello, everyone. Today, we're going to do our first ML Real Talk, talking about computer vision. Shreya Rajpal is a senior machine learning engineer. She was a founding engineer at Predibase. Previously, she worked at a special project at Apple, led a large effort to scale up the data capabilities of cross-functional ML team. Prior to that, she worked as a software engineer at drive.ai, worked on deep learning perception models for LiDAR that are currently in production at all drive.ai locations. Today, we'll chat about our experiences in computer vision, how to optimize compute, how to evaluate model performance, and how to iterate your model and bring them to the next level. Thanks for joining me, Shreya.
Yeah, I'm really excited to be here. Thanks for inviting me, Daliana.
So how did you get into computer vision?
I got into it like during my master's. Basically, I was working on research in essentially crowdsourcing and building confidence when you have a set of unreliable workers and you want to get labels from them to get to essentially build like good data sets. And then part of the domain that I started working on was getting data set and getting agreement between crowdsourcing workers for image data. And then as part of that, I started doing like some deep learning on computer vision, like basically on images, etc. I really enjoyed it, and then decided to like change my research to kind of focus entirely on that. So did a little bit of research in my master's on essentially fashion data sets, for example. So we had like a big fashion data set from Polyvore, and we would embed those data sets and try to figure out like relationships between image models, like what types of like different black skirts look similar to each other, different white shirts, for example, look similar to each other, what pairs kind of go together. So that was kind of like the type of research that I was working on. But it was just really fun. I really enjoyed working on it. And then after I graduated, I went to a self-driving startup, which was called drive.ai, where I basically did computer vision on image and camera and LiDAR, etc. So that was my journey into it.
Yeah. And I know you worked on some very cool project, Apple special project that you probably signed an NDA and you can't talk about it. So let's talk about the project you worked on at Drive AI. So can you give us some example of what type of data set you're dealing with? What are the challenges you are trying to solve, and what are the results you achieved?
So while I was at Drive, basically my job was to like train the perception system that would run on the car. So the idea was that so for people who are familiar with the self-driving stack, they would know that the perception team is the team that sits closest to the sensors. So the input to the team would be like all sorts of sensor data, like radar, LiDAR, camera, etc. And then the output from the team would be, a map with like objects on the map where you have like information about like what type of object is this. Is this a car? Is it a pedestrian, etc.? Where is it? Where is it heading? What's the direction in which it's moving? What is the velocity, etc.? So like a lot of metadata associated with each object. So on that team, yeah, basically my job was to do that object detection. So I didn't work with radar, but I primarily work with lidar and camera. And given those sensors, given that sensor data, I would like transform it into a format that could be consumed by a computer vision model, and then write code in TensorFlow or PyTorch that would try to get like as good a performance as possible on that data set that we cared about. And so the output would really be this like deep learning model that would then get optimized and like to be deployed on the car.
Yeah, cool. So what are some challenges in this project you have faced, and how did you solve those?
I think there were I think the main kind of like challenges around self-driving, for example, are like there's this very long tail of scenarios that are harder for cars to handle, and like for self-driving engines to handle, and how do you kind of like have better, more robust performance for those cases. And so, for example, like one of the like I spent like a lot of time, like a really large amount of my time dealing with this at Drive, which was our performance on trucks was like needed to be iterated on. And so trucks in the data set, if you think about it, are just rare enough where you don't see trucks as often as you see cars. And so if you would see a truck, more often than not, the deep learning systems would kind of like assume that this is maybe like 3 cars like lined up behind each other instead of like a single truck. And so you'd kind of like try to basically iterate on that, etc. And because this is, I think the big challenge for like how this is different from computer vision for applications like e-commerce, etc., was that like collecting that data would be very hard. Like there weren't a lot of techniques for like literally, if you wanted to like improve on this, you would like have to go like drive around more trucks, or instruct the data collectors, like the people who are driving these cars and collecting more data for us to train on, was to like try to go to areas that have like more trucks and try to get like more truck data points in the data set, and then kind of like improve on them, etc. So that was kind of like specific to the self-driving domain. I think that was probably getting like high quality data was probably the biggest challenge. I think some other challenges were basically around like evaluation, comparing different models, etc., those types of things.
We'll definitely talk more about model evaluation and metrics. So I think in computer vision, there's always also a challenge in the part about compute. How do you optimize it? How do you make sure you leverage all the resources you have?
I think that's a really good question. So I think the hard thing about computer vision, like I work more with other modalities once I came to Predibase, but like and this became like very obvious to me once I kind of started working with like tabular and text, was like just how much compute images need compared to any other data. And so I think like optimizing compute and making sure you're getting the most like bang for your buck like from the compute that you have is pretty important. So what I would typically do is like train on multiple GPUs and try to basically do like distributed training on each GPU. I think like the things to kind of look out for are that you're getting like highest utilization possible from that GPU. And so you really try to like look. I think the way to kind of go around it is to monitor GPU utilization, and then have like something like, okay, if at all points it should be greater than 90%. If it's dipping between like 60 to 70%, then there's like inefficiencies in how you set up your pipeline. That could be improved, and you would get a model that trains a lot faster, which is important because this compute is very expensive. And so setting up like distributed training appropriately, so that you're able to like there's no inefficiencies in like how you're loading your data, and how you're maybe like doing some of this aggregation, etc., of weights. I think like all of that is kind of pretty important to make sure that you're getting the most. So yeah, I would say that distributed training and like making sure that distributed training is very smooth is probably the biggest thing.
Yeah, and you mentioned it's important to monitor the utilization. So, for example, what are some practical tips you can give us? How can we monitor the GPU utilization?
Yeah, I think like how I would typically go about it is I would attach to the machine that actually has the GPUs and is running the training jobs, and just so there's an if you're using NVIDIA GPUs, there's this CLI tool called like NVIDIA SMI that prints out the state of the GPU at any given point. So you can kind of see utilization, you can see temperature, you can see how much memory is occupied by the model that is training right now, and maybe I think a few other things. And so I would literally just I would literally watch it as my training job
Mhm.
is going on. I think there are other kind of like techniques to do this. So for example, like some experiment management platforms, they basically if you hook up to that experiment management platform, then you kind of like are able to monitor this. There's a graph that you can kind of monitor automatically. So that's kind of like another way to do this. Yeah, but
Yeah.
it's very boring. You just kind of like, as you're training, you kind of like keep babysitting these jobs and like make
Mhm.
sure that they're training well. Yeah.
Yeah, I remember when I was working on some machine learning projects, I would kick off something, and then just over the weekend, I don't have to do any work, but I need to just check to see, whether it's failing, whether, like you said, other than a failure in the GPU. I like what you mentioned. You do need to babysit your model a little bit.
Yeah.
And
Yeah.
previously, you said it's good to make sure the GPU utilization is you want it to be higher than 90%. Say if you see the utilization is 60 to 70%, you mentioned you can do something on data pre-processing model pipelines. Can you give us some tips about where do you look at, or what do you do when the utilization is low?
Yeah, I think it's a great question. It's also like Luca from the audience, it sounds like, has basically the same question. So, yeah, I think I think the most likely culprit, like most of the times, is like your data prefetching, or like how you're loading your data in. So more often than not, if you're kind of like seeing, peaks and valleys, it's that the GPU kind of like processes one batch, and that is where you'll see that higher utilization. And then before essentially before the next batch is ready, before it can so that it can start computing on it, it's just like kind of sitting idle, and so the GPU utilization kind of tends to go down. So that is like, there's like other kind of like inefficiencies, but for the like, yeah, the majority of the times, like it's going to be like something around that, like something around optimizing your data loading, and data prefetching, etc. And so my suggestion would basically be to yeah, just try to like basically have like a parallel data loader queue, that it has capacity, so that like you're essentially like prefetching, pre-processing your image batches in the background, while the GPU is like processing like a batch. And so you have all of the pre-processing that you need to do on your next batch, like already done and stacked up, etc. And there's like some parameters. So like ideally, the way to think about queue size is that there should always be enough batches in the queue without overwhelming the memory of yeah, either the CPU or the GPU, like wherever you're kind of like doing this. So that would be the most likely culprit. I think if it's not that, then like some other things are like any post processing that you have to do, but just kind of be mindful of like essentially any processes that are IO bound, that need to happen for each batch that your GPU is training on. Like I would basically think about like parallelizing those, or like offloading them to the CPU, so that the GPU is only like, yeah, just being like very efficiently only focusing on the matmul operations for in like a PyTorch implementation of a model. parallel or something. So that's yeah, how you go about it. And also more concretely, I would recommend, so at Predabase, for example, like we used to while I was at Predabase, we used to use Ray, and I think that's still the case. I'd be very surprised if that changed.
Yeah.
But Ray is, Ray's like data library, like ray.data, or things like torch, distribute data parallel, etc. Like they already give you a lot of these utilities that kind of help you optimize your data loading and data prefetching, etc. So yeah, I'd recommend like checking those out. Yeah.
Hmm. Yeah. I'm curious. So, have you used Ray before you joined Predibase?
I had not. I think I had like a colleague who'd used RLlib extensively, and was had like really great things to say and everything, but I hadn't used Ray.
Mm.
Yeah, I think I started using Ray while I was working at Predabase, and yeah, I mean, I'm a big fan of Ray. I think it's
Yeah.
really makes a lot of things
So,
related to deep learning very easy. Yeah.
yeah. So, how do you compare your projects with Ray versus when you need to use some other libraries or write your own code to do distributed training?
Oh, I see. I would probably not write my own code ever again. I think it's generally like kind of like, harder to manage. Um, yeah, essentially, like there's a lot of, um, it's very finicky, essentially, the code for
Mhm.
distributed training if you are implementing it yourself, right? It basically means you have to kind of like you have to keep syncing up the weights. You have to make sure that each replica of the model is synced up and your models aren't diverging, etc. And there's like some other things to manage as well, like scaling learning rate, etc. And in general, like it's not a trivial code to write. So I would 100% recommend like only using a library. Like I think maybe in like 2016 or 20, even up to like 2017, etc. It did make you might have had to write your own distributed training code, but like now it definitely does not make any, yeah, like I would never basically write my own distributed
Yeah.
training code. I would only use Ray or like Torch DDP essentially.
Hmm.
I think like between the two, I think like Ray is definitely the more yeah, it's I guess it's a more what's the right word to describe it? It's more complete. For example, like if you think about like data loading, etc. as well, which is an essential component of this. So Ray offers much more flexibility that scales up to like really large data set sizes, etc. compared to something like PyTorch. So yeah, if you're just getting started with it, etc., I would recommend using something like Torch because the learning curve is very easy there. But like for like serious production ready applications, etc., depending on your use case, I think like Ray. For example, at Predabase, we use Ray instead of Torch GDP. Yeah.
Yeah. Thanks for sharing that. And previously during our chat, you talk about there are some hyperparameters you can tune to improve GPU utilization. For example, uh, dimensions of the images. Can you talk more about that?
Yeah, so I think the general kind of rule of thumb is that there's like some of these like image dimensions, etc., where essentially powers of two. So your dimensions kind of should always be powers of two. Your tensor dimensions. So as your images kind of like pass through the network, it kind of like it pools. Like there's often like pooling operations, etc., on images and a bunch of other things that change the dimensions of images. So always try to have it so that it's like powers of two, and generally that tends to lead to like higher GPU utilization. So I think there's a few like tips and tricks like that you can find online. I think that is like probably the most obvious one that I recommend. I think there's other ones. I think recently I might be misremembering this, but like Andre Karpathy or someone shared that they saw like huge gains in the time to train a model by just changing. I forget where it was. Like either the tensor dimension or the bat size to the nearest power two or something, and that kind of like really helped. So yeah, there's like, for example, libraries like Torch Image, etc., or other like pre-processing image pre-processing libraries like Pillow. They offer these functionalities that allow you to resize images. So yeah, would recommend basically using those to try to get the best performance possible.
Yeah.
Yeah.
So to look at the tensor size, the batch size, and then the size of the images.
Yeah.
Yeah, which is unique to the computer vision use cases. Cool. And it's also, besides training and data processing, the inference also takes a lot of compute power. So how do you save costs in running inference?
Yeah. So I think there's like I can talk about like what I've done in the past.
Sure.
I will say that I don't know if this is unique to computer vision. I feel like it might, apply to like general deep learning, across the board. But like often there's, like a few things you can do basically around like pruning the weights. So you kind of like, essentially the idea is that you train a model and then each parameter of the model, not all parameters have like a high weight or actually have an effect on the output, or on the final prediction or something. And so once you're like done training, what you can do is like do these like iterative sets of passes on the model weights itself and try to figure out like what are the model weights that you can just like zero out or just not have to pass any tensors through those, so that you save on kind of computation, and you can just like prune the model down and like get really good results. I think in general, like there's I think I'm a little bit rusty on this. I might be misremembering these numbers, but like there was some studies where, for example, you can, yeah, I think you can basically prune like, I'm like, yeah, I don't quote me on these numbers. I think I didn't prepare like the exact like
Yeah, no
numbers,
worries.
but yeah, I think you can kind of like, I think up to 50% of the weights without, with it, like you can prune like up to 50% of the weights of the model, let's say, without, changing more than like 1 to 2% in the final like metrics or like accuracy or something
Oh,
that you.
sorry. Could you say that again? I don't think I caught that.
Oh yeah. So I guess the idea is that you can prune like up to 50% of the weights of the model, for example, without changing, without it impacting more than like 1 to 2% of the model, like final metric, like accuracy, etc. So you can like really shrink these models down, like once you've actually found like a good set of parameters that kind of work well. So yeah.
20%, 25%, do you mean like doing dropouts on weights?
No, like after training, essentially.
Mhm.
So after training, you kind of like do a pass where you look at each model parameter and you figure out like what has, like which parameter basically is like close to zero and therefore has a negligible effect on the final outcome, like the final
Mhm.
tensor that is created.
Yeah.
And then, you can kind of like just like skip over those specific parameters, and therefore you end up like saving a lot of like computation or a lot of like matrix multiplication operations.
Oh,
Yeah.
gotcha.
And
Oh,
then
okay.
yeah, this is on the weights, and then there's like there's like a bunch of research around this, but like what you kind of find is that like you can kind of scale this up so that like you can start looking at this like per layer, for example, like what layer doesn't have an impact in the final tensor that is created, etc. And then you can like start removing layers, or you can start removing this like per filter, etc. So you can like aggregate these weights in different like at different levels of abstraction. Like you can go higher up like the grouping, and then the more you kind of remove, the more efficient the model is, but also like it
Yeah.
tends to impact performance a little bit.
Oh, okay.
Yeah,
Gotcha.
but
So
that
you're
is
trying
yeah.
to look at the value of the weights, and then you want to remove the smaller ones, so you kind of make the whole market architecture leaner.
Yeah, exactly.
Yeah.
Yeah, I think that was it's actually a pretty fun kind of like work stream, because you get the model, like I guess like one basic common workflow is like
Mm.
you train the model where it's like really super powered and like performs really well and everything, and you get the numbers that you want to hit on your test data set or whatever. And then after that you kind of like start shrinking the model down and think about like what is the smallest that I can get this
Yeah.
model to now without it impacting performance. So it's this interesting like kind of push and pull.
Yeah.
Yeah, I think some other techniques are basically around using like lower precision of the yeah, Zed's, sorry, I'll just respond to a question very quickly. Not exactly like feature selection. I guess it would be yeah, I guess it would be more of just kind of like so you still pass in the full image, you just kind of like in the internal nodes of the neural network, you kind of, like prune some things out. So I'm trying to think of like an analogy to, like tabular data, etc. But I can't think of a good one right now. I think like it would be similar, for example, for a decision tree where you're like pruning some branches of the decision tree or something like that.
Mhm. Yeah. Okay. Yeah, that makes sense.
Yeah.
Yeah. Well,
And,
if you have more questions, we'll get to that after the session. So,
oh, gotcha. Okay.
yeah. So
Um,
I think yeah, what you're saying is basically say if a model has three layers, but you notice one layer doesn't really do much, so you can maybe remove the layer. But I guess there's some work you need to do to kind of make sure the dimensions still work because there's all the tensors, right?
yeah. I think that's why, like, for the most part, people kind of do this like on a parameter level. Because also, if you remove more like a layer, that tends to, impact the final metric a lot more.
Yeah.
Um, there's like I think lower precision was another one. So right, like typically you have like 64-bit, each like neuron is like a 64-bit float, and then you can basically go to like half precision, like 32-bit or like 16-bit, etc. And then that, immediately leads to like much faster, like you just half or like quarter the memory used in the model, right? Like without too much without like doing too much work, like as you would have to do with pruning. And yeah, that's pretty effective as well. I think I was like talking with some researchers who kind of like worked on taking this to the extreme, wherein like this was like binary neural networks. And then each node in the network would basically be just a binary, like it
Mm.
would be either like a zero or a one. And then essentially, even with that, you would kind of find that like, yeah, it definitely impacted performance, and you go to that extreme. But even then, you're able to get like, some signal. So just reducing precision, and you can figure out where you want to stop is like another kind of like technique as well.
Interesting. Yeah.
Yeah.
Yeah, maybe after the talk, I'll ask you to help me find those papers. It's definitely very interesting.
Yeah.
Yeah, so okay, so here's compute, and you also talk about model evaluation. So, what are some metrics you usually use to evaluate models?
Yeah, so I think like it would depend on the use case. So I used to work on like object detection, for example, and like what I cared about was, or what my team cared about was that we're getting all of the objects that are around us, in like in a in a state in which the car is in, like getting all of the objects essentially, and then B, making sure that like for all of the objects that we're getting their dimensions accurately. And so essentially for me, the metrics were around, like we try to like how many kind of just like how many objects did we end up finding out of the total objects in the scene, and then B, like like metrics that kind of capture overlap between the predicted bounding box and the actual bounding box, etc. So that is where, that's the metrics that I personally cared about. But yeah, they would be very use case specific. Yeah.
Mm-hmm. Yeah, and in computer vision models, if you want to understand the model performance or do error analysis, um, I think it's different from tabular data where you can just get the aggregated metrics, precision, recall. You need to look at IOU, and you also want to understand how the predicted category associated with the ground truth. So how do you do those type of deep dive into specific examples versus looking at the aggregated metrics?
Yeah. I think that's a really good question. So I think this is like basically generally part of my workflow, but I feel like for any machine learning, but I feel like for computer vision, it makes, it especially makes sense because, it's so hard to have like it's so hard to like ask interesting questions from the data that
Mm.
give you as a developer insight about, okay, what should my next steps be, or if I'm getting any errors, are those errors, like, is it okay to have failures on those types because it's, there's like some extenuating circumstances, or some like outliers or something in that data, or is it like errors that I can actually improve upon because, or I must improve upon because, they're like going to be common errors, etc. So yeah, there's like ways to, there's like every in general, like every experiment would have a scalar metric that we were kind of tracking. So like IOU, like you mentioned, was like one of the ones we used to use a lot, or like precision recall, etc. But then the thing that I found like really essential to my workflow was, like exploration tools that would allow me to, add, basically do like fine grained slice based error analysis. So I would basically like slice up my data based on, what are the questions that I actually care about answering from my data, and then, use that to get an understanding of like, is my model any good or bad. So as an example, like I talked about, trucks versus cars versus pedestrians, etc. And then at Drive, what we would have is that, we had this like really nice internal tool that allowed you to kind of like, each bounding box was tagged with the ground truth data, and you could like slice up your data and like only show me examples where there's a pedestrian, within 10 meters of the car. And then, for those data points, like maybe because if pedestrian is super close to you, you really care about getting those right. You would get a sense of like, okay, what are the aggregated metrics, for these numbers, but you also get a sense of like my workflow would typically be ranking on that slice, like ranking what are the highest errors that I'm making and trying to understand why I'm making those errors. And let's say the slice of like where a pedestrian is very close to the car, I care a lot about this, right? So I would take these slices and then, like study them, like really like kind of like touch and feel the data, look at the camera, look at the LiDAR, and figure out why this error is happening, and then try to like, update like some hyperparameters of my model to kind of like fix this error and, make it go away essentially. So I would recommend like, I think this workflow of like slice based error analysis is generally pretty useful. Not all examples in your data set are equal. You should definitely, like, more often than not, you care about some types of failures a lot more than the others, and being able to like bake that into how you do error analysis, how you figure out if your model is any good, is like generally pretty useful. But especially for computer vision, because it's hard to like, it's so visual, like having tools that allow you to really kind of like plot that data and study it is something that I would recommend highly, and was very effective for me. Yeah.
Yeah. So do you use any exploration tools, metrics, dashboard, or did you create your own?
We did use exploration tools. So I think like I'm trying to think about like yeah. So at Drive, for example, we had a team, like there was a short sprint in which like a couple of members on the team, hacked out this like internal tool that we used, which was like pretty interesting. But I think in general, I feel like now the tooling space around this has like improved significantly. So I think like things like Streamlit, etc., make it really easy to build these dashboards, right? That like hook it up to your data frame, that you're storing all of your data in, and then kind of like create these filters that allow you to slice your data and everything. I think there's like other tools as well, like there's like now multimodal data, specific data frames. So for example, there's things like Meerkat or Daft, etc., as data frame libraries that allow you to like you would for tabular data, you can also see like images as tables, and then like explore it and like maybe group and aggregate images as well in interesting ways. I think there's like other techniques as well. So the tooling space generally has like increased significantly. And so if you are working on computer vision, and even if your team doesn't have an internal tool like my team did in the past, I would recommend basically using any of those, either data frame libraries, or like visualization or tooling libraries, etc., to kind of like set up your own thing, and it should be pretty fast. Like you should typically under a day to kind of do something like this, and then that day's worth of effort, is like a big multiplier that like really helps you along the way a lot. Yeah.
Yeah. That's a great advice. So when you look at model evaluation, and then so when you evaluate a model, you identify some issues, say in a small category or in general. How do you iterate the model?
Yeah, so I think it would depend on the type of failure.
Mhm.
So I'm going to keep with the example of trucks because I spend so much of my time at Drive. We're just working on getting trucks to work well, and it also, I guess, it's very easy to interpret as an example. But like for example, for trucks, I mentioned the issues with collecting data for trucks or for self driving in general. And so generally in computer vision, there's data augmentation, which plays a huge part, and especially compared to other types of data modalities, like for tabular data, etc. It's much harder to do data augmentation than it is to do computer vision because there's like some properties that remain consistent. So for example, like common data augmentation techniques, like rotating the image. So if you think about where a car is, even if you kind of like rotate around the center of like where the car is situated, if a pedestrian is like kind of like 10 meters to your left versus 10 meters to your right, the car's behavior should kind of stay the same, right? And so you can kind of like augment your data and create like multiple augmented examples based on that one initial example. Other things like mirroring the image, rotating, translating, etc. These are like basically common techniques in computer vision. And so if you find that there's like some slices or some types of data that is causing like a lot of failures. So for example, for my case, it was trucks, and I would augment examples that have trucks very significantly. So I basically try to create like as many like fake truck examples as I could. I think like other things were I would try to iterate on like the loss, etc. So for example, if I think that this object has height or width like greater than some dimension, then I would basically try to give those types of examples like higher weight so that the loss is higher if they tend to do poorly. I think other techniques that are more generalizable are just generally trying to balance out your data. So try to, for example, like if there's errors happening because some types of data is in the minority, so try to like oversample it or undersample the majority class, etc., so that you kind of do that, or try to use like specialized architectures that do well for those failure cases. Yeah.
Mhm. Yeah, thanks for sharing that. And so when you iterate a model, I know machine learning model would never have 100% accuracy. So how do you know when is good enough?
Yeah, that's like the $1 million question, basically. I think it's pretty hard. I think like it's pretty hard, and it's hard for me to answer that question as well because it's so use case
Yeah.
specific. I think like what I would kind of like think about is like I said, just kind of like having like building that deep understanding of your data set, by doing this exploration and by doing this like really fine grained evaluation, that I talked about earlier, like that kind of, in addition to just the actual like aggregated statistics, etc. It gives you this like understanding about like what does the model do well on versus what does the model not do well on. And that, I guess, is a very use case specific question, like are you okay having that type of risk? Or so for example, like I think for us we kind of found that like if within like some radius of the car we generally were pretty good, and then as the object tend to get further away, or as the object was like trucks that were far away, for example, was a very hard thing. So so in some sense that's like okay, this type of risk is acceptable versus this type of risk is not acceptable, and it kind of like depends on your use case and like what's yeah
Yeah.
yeah.
Yeah, I think that's a great point. I remember giving presentations about performance of computer vision model. You don't want to just put aggregated metrics there. You want to show stakeholders some examples. Hey, maybe on the trucks, this is show an image. This is the truck looks like. This is what model predict. I think to demonstrate that you understand in some cases the model doesn't perform well, and let a stakeholder know it's a way to earn trust, and they know it's not going to be 100% accurate, and then they can assess can they tolerate this type of risk? Are they willing to say put a model in shadow to test that, put it in production? So yeah.
Yeah, exactly. And I think especially for something like computer vision, right, more than other data modalities, because once again, it's so visual and it's very, it's very easy to kind of like, like you said, like if you're talking to stakeholders and if you show the images and, this is why these images don't work well versus this is, an average image, and that's something the model does well on. Like, I think that is, very easy to kind of like, it's very intuitive as a, third party to understand as well. Yeah.
Yeah. So say now you are good with the model, you want to put the model in production. What are some best practices about computer vision model in production?
Yeah, I think that's a good question. So I think like I don't know how relevant my answers are going to be, very frankly, because I think I think like I worked in self-driving where, at drive.ai, for example, where the model would always need to be deployed on the cars that we had at drive. And so, like some of the concerns, like it would be different than, if you're deploying a computer vision model like on the cloud and you need to kind of like query that model,
Oh,
etc.
okay.
So some of those considerations are different. But like, for example, like for us, like one of the most important things along with just the performance of the model was also the latency of the model, or the memory of the model. There's only like finite compute available in the car, and the end-to-end latency for a drive vehicle to like make a decision once it like spots something like a pedestrian, like needs to be lower than some threshold, right? For the car to be able to function. And so we would basically have we'd essentially kind of like think about, okay, this is the latency budget that I kind of need to get this model under. This is the memory budget because this is the only GPU that we can fit on a drive-by vehicle. And so, just kind of like trying to get it, under that constraint probably was the biggest consideration for us.
Yeah.
Yeah.
So do you usually learn about the constraints at the end of the project, or say halfway you feel you have some confidence about a model, you start to talk about model in production?
I would typically I would definitely ask this at the start of the project. Like I would get information about like what is the budget that I'm working with here in terms of in terms of like compute, in terms of latency, etc.
Yeah.
I will say that like for deep learning generally, and I guess even for specifically for deep learning, because there's so much you can do after you train a model to try to shrink it down, and there's a whole field of like research and studies on it about techniques on how to do this. So yeah, basically I think like something that works really well for deep learning is to get an idea of the constraints and then try to like max out, try to think about like if constraints like weren't an issue, what is the best model that I can train for this data set. And then after you have that model trained, basically like try to start shrinking it down. And there's like insane statistics out there about like with like 20% of the model's memory or the model's latency, etc., you can like definitely shrink the model down. So would definitely recommend people like look into that research, but get an idea of the constraints beforehand, then ignore the constraints and then try to build the best ML model possible. And then once you know what is the best thing that is possible, then try to get the model within those constraints. So that would be my workflow.
Yeah, this is a great advice. I always recommend folks to understand the production use case even when in the very beginning of the project, so you know where you're working with. And also, like you say that, but when you build your first model, when you try to iterate, forget about the constraints to see what is the best one you can get. Because if your first model, if you already try very hard, try everything using a lot of resource, your model still doesn't perform well, that means with the constraints, it's going to perform poorly. Maybe that's a quick way for you to decide, oh, I need to pivot. I need to work with something else.
Yeah, exactly. I think like
Yeah.
getting that early signal about, is this a problem that machine learning can even solve? I think is very important. So to that point, like I think like one thing that you'd often like is if you're starting a new ML project or a new computer vision project or something, like always try to subsample the data and then really overfit the model like only on that tiny subsample, and make sure that you're able to see like 100% training accuracy or something like that, to make sure that in general, like this data has enough signal that a fully overpowered machine learning model will be able to get good performance on it, and then start adding the data back, start increasing like or decreasing model complexity, etc. So yeah.
Okay, interesting. So is that in the beginning, it's okay if your model is a little bit overfitted because you want to see whether the data have signal, kind of basically quickly test your hypothesis.
Yeah,
This model is trainable. Yeah.
Exactly. Yeah.
Cool. I learned a lot from your advice. I feel you only get this type of information from someone who has done it. My last questions before we wrap up is, what do you think is missing for today computer vision?
Yeah, I think that's a good question. Um, I would definitely say like, introspection tooling. Like I said, like computer vision is a difficult modality to, work with because of how expensive it is, how much, compute you require, etc. And then also how hard it is to do error analysis. And I think like standardized tools that make it very easy to understand how to iterate on your models, I think like, those types of tools would be helpful. So for example, like if you're working with tabular data, like often your workflow is, working in a Jupyter notebook, training a quick model, and then printing out like a pandas data frame that, allows you to quickly figure out like, where things go well, where things go poorly, and, like just that iteration speed is so fast, right? That you're able to kind of like be very productive in that data domain. Computer vision is very different. Like it, for example, I spent days training models, and I spent a very long time for a single model analyzing it and like trying to figure out if it's good or not. And so I feel like tooling that makes it easy to kind of like understand, what's happening within a model, that like is this model any good, is this a good data set, can I get any more lift, etc. I think like having more adoption of the tooling or having better tooling, I think would be like really really awesome. Yeah.
Yeah. So what, for example, what type of tools you recommend, or you think people should consider play with? Say, for example, Streamlit you previously mentioned. What are something else?
So I think like Streamlit and Radio are really good. So Streamlit is something that I've used, extensively in the past to kind of like spin up quick dashboards. For example, like the internal dashboards that I was talking about that the team kind of hacked on for weeks, like something like that can be made like very quickly in the order of a day or so. I think like now there's actually a really cool set of these tools that people can use. So I think like some new, for example, like computer vision, essentially it's like some new dashboard tooling. So for example, Pinecone is this other alternative that allows you to kind of spin up these dashboards very quickly. I think also like data frame libraries that make it very easy to work with data modalities outside of just tabular data. So think about like how amazing and how effective something like pandas is, right? If you're working with a tabular data set. So libraries that make it easy to do that, but for computer vision, I think like would be, I think there's been some recent advances and like more adoption and more like development, etc. of those would be really nice. So I think my suggestions. Yeah.
Cool. Thanks for sharing that. And we have a few more questions. So what I'm going to do is, Shreya, you might want to, drink some water. I'm going to give a quick demo on how to use Predibase to train a computer vision model and do iteration. And then we'll be back to answer some questions and maybe also talk about what Shreya is up to today. Okay, are you able to, you can see my screen. So Predibase is a declarative machine learning platform and I'm going to show you what it can do to train a computer vision model. So it's very easy for you to connect your data. You can upload from your local files or wherever your data lives. And for a computer vision data set, we're going to upload our data into S3. And you only need to tell Predibase, for example, where is the S3 data source. So this is a data set we already uploaded. You can see the images here. Is very easy for you to preview the data. And the use case today is a very fun one. We want to classify whether image is standard or not. So you can see this is, there are some labels that are standard. There are some could have the potential to be standard or not. And once you have your data connected, you can go to the model tabs and create your model. You want to make sure you have the right connection data set. So here, because it's a computer vision model, we are selecting neural network as the model type. And if you are using tabular data, it's also easy for you to train a tree-based model here. So here you can have the feature. So the image path would be the feature. We'll render image in your S3. And we also have the labels here. So once you're ready, you can go to next. Here you can use suggested configuration, which is similar to AutoML. And you can also just start with the basic default. So here we, based on your input feature, output feature, will suggest a basic model graph for you. So previously, Shreya mentioned that to improve your GPU utilization, you can play with some parameter. For example, when you pre-process image, I want to show you, it's really cool that you can change the image height, weight, input your parameters here. You can, here we use the stack CNN encoder. You can also select one you think you want to try. And so this is a great way for you to specify parameters based on models' different training stage. And you also can do this through in the config file. So if you're familiar with the open source project Ludwig, if you want to do this in Ludwig, this is the YAML file you want to use, and you can add additional, say, trainer informations, epochs, learning rate, etc. So for example, you can change learning rate here, image. So this is kind of equivalent to what I showed you before in a model graph. If you want to, say, update all your hyperparameters here, there's a lot of things for you to play with. So in deep learning models, we always run a few different iterations, run different experiments. You want to see which one performs well. So this is a great way for you to test your ideas. So once you added your hyperparameters, you can click train. And I want to show you once the model finishes training, it will show you it's ready. You can click into the version. So this is a dashboard. You can see the learning curves or model, how accuracies converge over the epochs. And we also show you, you can also see the config model graphs here, confusion matrix. This one performs pretty well. We're able to tell which one's standard, which one's not. ROC curve, precision recall. Yeah, so this is a model dashboard, and you can also click into the data set if you want to take a look at the data again. So yeah, this is just a quick overview, and if you are interested in a demo, you can request a demo here. All right, let's come back to answer some questions. So Shreya, Someone's asked about data quality. I think that's an important one. How do you make sure the data quality is good?
Yeah, I think that's hard, and it's harder in computer vision once again because of the you know because of how hard it is to kind of automate things around computer vision. So I think like in the past, depending on where you're getting your data from, if you have, for example, like a crowd of workers that is labeling your data, I think kind of one common workflow is to have like a subset of people that is actually doing the annotation, and then have a different subset of people that is checking if that annotation is correct or not. And so that allows you to just do some intelligent, basically aggregation things about making sure when things are correct, etc., when you can have confidence in the data label itself. So that is basically at the source level, right, of like where you're getting your data from. I think there's another level of like, okay, once you kind of have this data and you're kind of working with it, how do you kind of figure out what's happening and what's not? I think for that, the two I think the tools remain the same, just the workflow is a little bit different. The tools, I would once again, I'm a little bit worried that I'm sounding like a broken record here, but once again, like having like really great dashboards and like visualization tools are like essential for computer vision
Yeah.
development. I personally haven't worked in a team that does not have that, and I can't imagine having to, actually build and like continue to work on computer vision systems if you don't have those like detailed exploration tools. And so using those tools to when you kind of get the data, create slices and like figure out, how things are going, etc., like where the issues are, what different slices look like really develop an understanding of what your data set is. And I always like to say, like, try to like touch and feel your data, and like really see a subset of examples and like kind of build intuition. And I think the second one is like, again, using the same tools, but like doing, once you train a model, doing like slice based error analysis. So one of the common things that I would find is that like I would train a model, and then maybe the performance was not as good, etc. And once I would start looking into the examples that are driving down the actual performance, I would find that, okay, it's like mislabeled, or it's like maybe the bounding box is drawn weirdly or something, like any number of these things that make it so that like the model prediction is actually decent, but it's just considered like a failure because of the data quality issues. And so I think like even training a model and using model predictions as a tool to analyze like where things are going wrong, I think that is like very effective in uncovering data quality issues. So that would kind of be another workflow that I would recommend, using the same tools.
Yeah. And it doesn't have to be super complicated if you have to build it. You can simply build some function to print some examples, right? And also, like you said, how to make it easy for you to slice and dice the data.
Yeah.
Yeah. Someone asked, is there any open source tools, a recommendation for data labeling? Data annotation.
Oh, that's a good one. Is this like, maybe we can ask them like, what scale is this something you want to annotate yourself, or maybe share to a group of, like a crowd of workers that you want to employ or outsource to?
I think if you're outsourcing it, probably it's not going to be open source. Yes. So
Uh,
ask the question and annotate myself.
Annotate yourself. Yeah. I think, um, yeah, I'm trying to think. I do think that like, on the order of thousands of, yeah, sorry, in the order of thousands of images, I need expert researchers to do that. Yeah, I think that makes sense. I'm trying to think of some. um yeah, I think that my recommendation would be something like, it's a pretty new tool, and also full disclosure, I kind of know the creators of the tool. Yeah, I would say something like Meerkat, essentially, that allows you to kind of like build these interactive workflows. So essentially you can like, it's this like data frame library where you can like visualize like, okay, these are all of the rows in my data set, and these are the metadata, and these are the images, etc. And you can kind of click on an image and like select or subset, basically select it, subset it, or add an editable column where, okay, this is the image, and like maybe this is just a classification problem or something, so what the class of the image is. And you can also like draw on the image to, like, if you want to draw boundaries, etc. So I think that would be my recommendation. It is a newer tool, but yeah, give it a try.
Yeah, thanks for sharing that. I think someone, Mohammed, asked about scaling models in production. I think we talked about that, get the requirements before working with the constraints. Do you have any experience working with real-time inference?
Yeah. So at Drive, for example, if we were, running a deep learning computer vision model in production, it would need to run in real time. I think like at Drive, it was okay under 20, 100, under 20 milliseconds or something for genuinely a very large image, like a very large map size. And so I would, in order to basically get it real time, I would say there's like some model architectures that perform really well for real time data. So for example, I'm trying to think about like what it's called. Uh, so while I was at Drive, one of the models we used to use was called like UNet, which is a computer vision model which is like very performant, but also is like very very fast. So there's like a subset of these architectures that are optimized. They're not like state of the art, and they're not going to give you like the best performance objectively, but like going to give you the best performance, given the cost of doing that inference. So I would say, thinking about like what are the best model architectures, etc. There's a bunch of research on architecture search, like MobileNet, etc. was a paper that Google released, where it's like, okay, I want to run this computer vision model on something like a mobile phone, like how or yeah, I think that was what it was. Or I basically need to run this model given like very low latency conditions. How do I do that? So looking at like starting out with those sets of architectures would be my recommendation. And then
Yeah.
doing the other things like post processing, pruning, distillation, half precision, etc. Really helps get the latency down so that it can be like near real time. Yeah.
Yeah. And Alexis asked a great question. What are some good visualization tools for 3D data, such as point cloud mesh data that one can integrate in their training pipelines?
I see. Yeah, I think this is a good one. So I don't know about like the full set of tools. The one that I personally used to use was called Weights and Biases, which supports a bunch of different like visualization types. So I think you can you can basically visualize like any type. Like it supports like a huge amount of like data visualizations, and you can definitely visualize like any 3D LiDAR, etc. in that. So that is the one that I would recommend and that I personally used. Yeah.
Yeah, and speaking of data visualization, was meant to ask if you want to understand what the model is learning, what kind of features they're learning from. Do you do any visualization to help you understand the models?
Yeah, you can do things like heat maps, etc., on the raw image to kind of figure out, where the what are the pixels that are contributing to the final prediction. So that is like probably one of the most effective things. It like helps you figure out like where the model is actually, like what are the values that the model is actually using. So that was probably like, as in terms of explainability, like that was probably like I think the most effective thing. Um, Let me think. Yeah, I think like some other ones which were more for debugging, like visualizations to figure out, like how to debug my model, but like maybe not so much on the image itself, was to visualize like the distribution of like model activations and model gradients, etc., and like make sure they're kind of like normally distributed, etc. Like the values aren't too extreme, things like that. I feel like those visualizations, like if your model isn't, if your deep learning model isn't training well, like that's an easy one to look at and figure out like what you can do better. Yeah.
Mm-hmm. Yeah, thanks for sharing that. I think we are a little over time. Let's just take one last question. How can we train a model to recognize and distinguish between similar objects with high accuracy, even when the objects have subtle visual differences? or are viewed from different angles. Any vision related use case for supply chain, retail, particularly for product substitution?
That's a really good question. So, my a priori suggestion would be something like a triplet loss, etc. Like using a triplet loss, where not sure how many people in the audience are familiar, but I'm just gonna give a very quick explanation just in case.
Sure.
The idea is that each sample in your data set is a triplet of three examples. So let's say you have three images, where two images are very similar, but they actually need to be labeled as different. So you would include like two images that are actually the same and like should be grouped together versus and a third one that actually is different. And then you would have like these three samples as like one row of your batch essentially. And so what triplet loss tries to do is it tries to like group the things that should have the same label or something like close together, and like try to split the one that is different like further apart. And so you end up like creating these embedding spaces that have like some separation between like objects that are similar and objects that are harder. So there's like variations of this, etc. I forget what it's called. The Yeah, I forget the name of that loss, but the one that Chinese networks use. But basically, like these losses that allow you to like group examples to like that allows you to provide like, okay, these two examples that are very similar will have very similar embeddings, but they actually need to be different, and so the loss will be higher if their embeddings are very similar. And so you end up like back propagating like a high loss, and then end up changing the embedding so that you're able to separate them. Yeah, so that would be my starting advice basically. Yeah.
Cool. Thanks for sharing that. Okay, that's all the questions we're gonna take for today. We're gonna have more ML series, so follow Predibase LinkedIn account if you don't want to miss it. So before we wrap up, Priya, what are you working on right now? What are you excited about?
Yeah. Yeah. Uh, this is hilarious because I don't think you've ever gotten my name wrong before, and we've
Yeah.
worked together. Yeah, I recently quit my job at Predibase. I am just kind of exploring right now. I released an open source package called Guardrails, which essentially thinks about how to add guardrails and reliability and safety guarantees around deep learning models. So that's kind of like my focus at the minute. And yeah, trying to explore more in that space. Yeah.
Awesome. Yeah. If you're interested, check out Gabriel's AI.
Yeah.
All right. Thank you so much, Shreya, for joining me. And you shared so many great tips. I hope you all incorporate in your day-to-day work. That's it. Have
Yeah.
a great rest of your day.
Yeah. Thank you for inviting me, and thanks to the audience for sticking around, and hope this was useful. Thank you.
Thank you.